We are talking about the human eye.
We are.
It is, and this is not an exaggeration, probably the most sophisticated optical instrument you will ever own. And you get 2 of them for free.
Right.
And what we're diving into today is specifically the optics of vision. We're pulling from Chapter 50 of the Guyton and Hall textbook of medical physiology. It's kind of the Bible for medical students.
And I love this topic because it's not about the poetry.
No.
We are not talking about the windows to the soul today.
We are talking about physics, geometry, and believe it or not, fluid dynamics. We're talking about plumbing.
Which is such a great way to look at it because vision really does feel like magic. I mean, just think about the range. Oh, it's incredible.
I can be looking at a mountain miles away, and then in a fraction of a second, I can shift my gaze to a text message 6 inches from my nose.
And it adjusts instantly. No lag.
Done. It handles everything from blinding sunlight to a nearly dark room. It focuses, it tracks, it stabilizes. If you tried to buy a camera that did all that, it would cost a fortune.
And it would be the size of a suitcase.
Yeah.
And that camera analogy is perfect because that's really the central theme that runs through this entire chapter. The eye is a camera.
Or maybe the camera is a crude imitation of the eye.
That's the better way to put it. They are logically comparable. You have a lens system up front to focus the light.
Yeah.
You have a variable aperture, which is your pupil, to control how much light gets in.
Got it.
And you have the film, or the digital sensor, at the back, and that's the retina.
But unlike my camera, this one is made of, jelly and protein. It has to inflate itself with fluid to keep its shape, and it's hardwired directly into my brain. Exactly. So that's our mission today. We are going to break this optics of vision chapter down, really, line by line.
Okay, so where do we start?
We have to start with the raw material, the physics of light itself. Why does it bend? How does it move? From there, we'll build up the anatomy of the eye's lens system.
And we'll get into how we focus, that whole mechanism of accommodation, which is honestly a bit backward from how you might think it works.
It's very counterintuitive. And then we'll cover why that system fails as we get older. We'll look at the common errors: nearsightedness, farsightedness, astigmatism.
And how we fix them with a piece of glass.
Right. And then we'll finish with the plumbing,
Okay.
the fluid systems of the eye, which is where you get into really serious conditions like glaucoma.
It's a whole journey from pure physics to biology. So let's start at the beginning. Section 1, the physics of light.
Let's do it.
I think most people have this idea from school that the speed of light is a constant, right? It's the universal speed limit.
It is the universal speed limit, but that constant comes with a massive asterisk.
Oh.
In a vacuum, or for our purposes, in air, light travels at roughly 300,000 kilometers per second. It's an insane speed.
Hard to even imagine.
You could circle the Earth 7.5 times in a single second. But, and this is the absolute crucial part for all of optics, that speed is not maintained when light tries to move through transparent solids or liquids.
So when light hits a window or water or the tissue of my eye, it hits the brakes.
Hits the brakes hard. The source material notes that when light travels through something like glass, it slows down to about 200,000 kilometers per second.
Wow, that's a huge drop. A third of its speed is just gone.
Gone. Instantly. And this change in speed is what gives us our first big concept, the refractive index.
Right.
The refractive index sounds complicated, but it's just a ratio. It's a way for a scientist to put a number on how much a material slows down light.
And the formula is pretty simple, right?
Very simple. You just take the velocity of light in air, and you divide it by the velocity of light in whatever material you're measuring.
Okay, let's do the math. Air is our baseline, so speed in air divided by speed in air is just 1.
Exactly. The refractive index of air is 1.00.
And for glass, we take 300,000 and divide it by 200,000.
And you get 1.50. So the refractive index of glass is 1.50.
So the higher the number, the slower the light moves. The denser the material is, optically speaking.
Precisely. A diamond, for instance, has a refractive index of about 2.42. Light just crawls through a diamond, relatively speaking.
Okay, but here's the question that always bugged me. Why do we care? Why does slowing down make light bend? Because that's what a lens does, right? It bends light.
That is the fundamental question. If I drive my car from pavement into a patch of mud, I slow down, but I don't automatically turn left.
Right. Why does a speed change equal a direction change?
To get this, you have to stop thinking of light as a single beam, like a laser pointer. You have to visualize it as a wave front. The source material uses a classic diagram for this, figure 50-1, but the best analogy is a line of soldiers.
Okay, a marching band. I can picture that. A long line of them shoulder to shoulder.
Perfect. They're marching on smooth pavement, which is our air. They're moving fast. Now up ahead, there's a muddy field, our glass. And here's the key. They hit the edge of the mud at an angle.
Ah, not straight on. They're coming in diagonally.
Exactly. So what happens?
I see it. The soldier on the far left end of the line is going to step into the mud first.
Right. And the second he does, he has to slow way down. But the soldier on the far right end of the line, he's still on the pavement.
So he keeps moving fast for another few seconds.
Which means the left side of the line is dragging, while the right side is still surging ahead.
And the whole line pivots. It swings around. It turns.
That is refraction. The light ray bends because one part of the wave front slows down before the other part. It's a purely mechanical turn.
That is such a clear way to visualize it, and that also explains why light doesn't bend if it hits the glass straight on, right? Perpendicular.
You got it. In the marching band analogy, that would mean every soldier hits the mud at the exact same time.
They all slow down at once, so the line just keeps moving straight, only slower.
No pivot. So for refraction for bending, you need two things: a change in speed and an angulated interface.
Okay, so we have the mechanism. Speed change plus an angle equals a direction change. Now let's apply this to lenses because the eye is full of them. Let's start with convex.
Convex lenses, these are the focusers. They're thick in the middle and thin on the edges, like a magnifying glass.
So if we stick with our marching soldiers...
The soldiers in the very middle of the line are going to hit the thickest part of the glass. They hit the deep mud first and slow down the most.
While the soldiers on the outer edges hit the thin part of the glass, or they stay in the air a bit longer.
So the edges of the line wrap around the slow-moving center. All the light rays bend inward. They converge.
And the single spot where they all meet is the focal point.
Precisely. A convex lens takes parallel rays of light and brings them together at a single point.
So a concave lens must be the opposite.
It is. A concave lens is thin in the middle and thick at the edges. It's shaped like a cave. It goes inward.
So this time, the soldiers on the edges hit the thick glass first and slow down.
While the soldiers in the center keep marching fast through that thin middle part, this causes the line to bow outward. The light spreads out. It diverges.
Okay, that makes sense. But there's a third type of lens in the source material that's super important, but I feel like people don't think about it as much: the cylindrical lens.
This is absolutely vital for understanding astigmatism later on. So far, we've been talking about spherical lenses. Like a slice of a ball, they focus light to a single point.
Right.
A cylindrical lens is different. It's shaped like a section of a pipe or maybe a glass tube.
So it's curved in one direction, but it's totally flat in the other.
Exactly. So imagine you have a glass tube standing vertically. If you shine a beam of light through it, it's not going to focus that light into a dot.
Because it's only bending the light from side to side. It's not bending it from top to bottom at all.
Yeah, I got it. So it focuses the light into a vertical line.
Ah, so spherical lenses give you a point focus, but cylindrical lenses give you a line focus.
That is the crucial distinction. And because of that, a cylindrical lens has an axis. You can have it standing up at 90 degrees, or lying flat at 0 degrees, or tilted at any angle in between.
Which explains why my glasses prescription has an axis number on it.
That's exactly what it is. The optician is telling the lab at what angle to orient that cylinder to fix the specific error in your eye.
Okay, we get the shapes. Now we need to measure the strength of these lenses. This brings us to section 2, measuring optical power and the diopter.
The diopter. It sounds like a complex term, but it's really just the standard unit for measuring how much a lens bends light. It's refractive power.
And the formula, thankfully, is pretty straightforward.
It is. It's just 1 meter divided by the focal length of a lens, also in meters.
Okay, let's run through a few examples to lock that in. If I have a lens that focuses parallel light rays at exactly 1 meter behind it.
You take 1 meter and divide by the focal length, which is 1 meter. So 1 divided by 1. That's a +1 diopter lens.
Simple enough. Now, what if the lens is stronger? It bends the light really hard and focuses it at just half a meter, so 0.5 meters.
Then you do 1 divided by 0.5, and that gives you +2 diopters.
And a really powerful magnifying glass, maybe it focuses at just 10 centimeters, which is 0.1 meters.
1 divided by 0.1 gives you +10 diopters. So the takeaway is simple. The bigger the diopter number, the stronger the lens and the shorter its focal length.
What about the concave lenses, the ones that spread light out? They don't have a focal point in the same way.
They don't, but they do have the power to neutralize a convex lens. So we measure them in negative diopters. A concave lens that perfectly counteracts a +1 diopter convex lens is called a -1 diopter lens.
So if my prescription is, say, NIDIS 3.0, that literally means I need a concave lens with 3 diopters of diverging power to fix my vision.
That is exactly what it means. It's all about finding the right number to balance the error in your eye's natural lens system.
Now, before we get to the eye itself, there's one more piece of physics here about how an image is formed that is just mind-bending.
I don't know which one you mean.
When a convex lens, like the one in our eye, forms an image on the retina, what happens to that image's orientation?
It gets completely inverted. It's always upside down and reversed from left to right.
So just to be clear, right now, as you are looking at me, the lens in your eye is projecting an image of me onto your retina that is upside down.
That is 100% physically correct.
Mhm.
My feet are currently pointing toward the ceiling inside your skull.
So why isn't the world upside down for me? Why do I see you right side up?
Because the eye is just the hardware. The brain is the software. The brain receives that upside-down data feed, and in post-production, it flips it.
It's just trained to do that.
It's trained from the moment you're born to interpret that inverted image as an upright world. It's a learned correction.
I remember reading about those experiments where people wore prism glasses that flipped everything.
Yes, famous experiments. The glasses would optically flip the world upside down before it entered the eye, so the retina was actually receiving a right-side-up image for the first time.
Which, to the brain, would look completely wrong.
Totally wrong. The brain is expecting an inverted feed, so when it gets a correct one, it perceives the world as upside down. People get dizzy, they can't walk.
But the brain adapts.
Incredibly, yes. After a few days, the brain software rewrites itself. It creates a new patch, and suddenly the person starts seeing the world as normal again, even while wearing the glasses.
That is wild. It really shows you that what we see is as much a neural interpretation as it is an optical reality.
Absolutely.
Okay, let's stick with the hardware for now. Let's finally build the eye. Section 3, the optics of the human eye.
Right, so the eye isn't just one lens. It's a complex system with multiple layers. The source lists 4 specific points, 4 refractive interfaces where light bends on its way to the retina.
Let's walk through the path of a photon. Where's the first bend?
Interface 1 is when light leaves the air and hits the front surface of the cornea.
Okay.
Then it passes through the cornea and hits the fluid behind it, the aqueous humor. That's interface 2.
Yeah.
From the aqueous humor, it enters the lens itself, interface 3. And finally, it leaves the back of the lens and enters the main jelly of the eye, the vitreous humor, interface 4.
That's a lot of different surfaces and fluids. Trying to calculate the total bending must be a mathematical nightmare.
It is. So to make it workable, physiologists came up with a simplified model called the reduced eye.
A scientific shortcut.
Basically, they treat all those different surfaces as if they were just one single powerful refractive surface located about 17 millimeters in front of the retina.
And when they do all that math, what's the total power of a normal human eye?
The source gives the number as 59 diopters.
59! That is a seriously powerful lens system packed into a tiny ball.
It's immense.
But here's what really surprised me in this section. When I think about focusing, I think about the lens in my eye. But the source says the lens isn't even the most powerful part.
No, not even close. This is probably the biggest misconception about how the eye works. About 2/3 of that 59 diopters of power, so roughly 40 of them, comes from the cornea.
The clear front window of the eye.
Yes. The cornea does almost all of the heavy lifting.
Why? Why is the cornea so much more powerful than the thing literally named the lens?
It all goes back to our refractive index and the marching soldiers. Remember, the biggest bend happens when there's the biggest change in speed.
Right.
The change from air, with its refractive index of 1.0, to the cornea, with an index of 1.38, is a massive jump. The light slams on the brakes and you get a huge, powerful bend.
Okay, and what about the internal lens?
The internal lens has an index of about 1.4, but look at what's surrounding it. It's floating in aqueous and vitreous humor, which are basically water. Their index is about 1.33.
Ah, so the jump from 1.33 to 1.40 is tiny.
It's a very small step. The light barely changes speed when it hits the lens. It's like our soldiers marching from deep mud into slightly deeper mud. They don't pivot much.
This perfectly explains why you can't see clearly underwater.
Yes, when you open your eyes in a pool, water is touching your cornea. The refractive index of water is 1.33. The cornea is 1.38. That massive air-to-cornea jump is gone.
You've basically neutralized the cornea. It stops working as a lens.
You've lost about 40 diopters of power, instantly. Everything becomes a hopeless blur. Goggles work simply by trapping a layer of air in front of your eye, which restores that powerful interface.
So if the cornea provides all the raw power, what is the point of the internal lens? Why is it even there?
Because the cornea is rigid. It's a fixed focus lens. Its power never changes. The internal lens is valuable not for its power, but for its adjustability. It's the zoom function on the camera.
Which brings us to section 4, accommodation.
The mechanism of focusing.
And accommodation is just the technical term for the eye increasing its power to see things up close.
That's right. The source says the lens can change its power from a baseline of about 20 diopters up to 34 diopters. That's an increase of 14 diopters of accommodation.
So how does it physically do that? I loved the balloon analogy in the text because the whole mechanism is really counterintuitive.
It's very backward from what you'd expect. So let's start with the lens itself. It's this little capsule filled with a thick, protein-rich fluid. And it's naturally elastic.
Okay.
If you were to take a young, healthy lens out of an eye and put it on a table, it would puff up into a nearly perfect sphere, like a little water balloon.
So its natural resting state is to be fat and round.
Yes, but inside the eye, that's not what happens. It's attached all around its equator to hundreds of tiny fibers called suspensory ligaments.
Like the strings on a trampoline.
A good way to think of it. And these ligaments are constantly being pulled tight, stretching the lens.
So when I'm just relaxing looking at something far away, these ligaments are under tension and they're pulling my lens into a flat, thin shape.
Exactly. A flat lens is a weak lens, which is what you want for distance vision where the light rays are already parallel. Now here's the paradox. To see something up close, like a book, you need a stronger, rounder lens.
Right. And to get that, we use the ciliary muscles.
Yes, but usually when you think of flexing a muscle, you think of it pulling something tighter.
Yeah.
The ciliary muscle is a sphincter. It's a ring of muscle that surrounds the lens. And when a ring muscle contracts, the circle gets smaller.
Like pulling the drawstring on a bag.
Perfect analogy. When that ring of muscle contracts, it moves inward toward the lens. And in doing so, it releases the tension on all those suspensory ligaments. The trampoline strings go slack.
So contracting the muscle loosens the strings holding the lens.
Precisely. And with the tension gone, the elastic lens is free to do what it naturally wants to do. It balloons out, becomes rounder and fatter, and its refractive power increases dramatically.
Let me just say that back to make sure I've got it. Muscle contracts, which means ligaments go slack, which means the lens gets fat, which lets me focus on things up close.
You've got it. And the opposite is true for distance. You relax the muscle, the ring expands, the ligaments pull tight, and the lens gets flattened.
Which implies that looking at something far away is rest for the eye.
It is.
And looking at a screen or book for hours is work.
It's a sustained muscular contraction. That's why you get eye strain. You're flexing a muscle for hours on end to keep that lens in its rounded shape.
And this is all controlled by the parasympathetic nerves.
Yes, from the third cranial nerve. It's an automatic process.
Now, this system is amazing until it's not. We have to talk about presbyopia, the aging eye.
The inevitable decline.
The statistics in the book are pretty brutal on this.
They are. A young child has about 14 diopters of accommodation. They can focus on an insect sitting on the tip of their nose. Their lens is incredibly soft and flexible.
But then what happens? By age 45 or 50?
That 14 diopters of accommodation has dropped to just 2.
And by age 70?
It's 0. Gone.
Why? Does the ciliary muscle just get weak?
No, the muscle and the nerves are usually working just fine. The problem is the lens itself. It's a protein problem.
What does that mean?
Over the decades, the proteins inside that lens capsule progressively denature. They change their structure, they cross-link, and the whole lens becomes hard and inelastic.
So it turns from a flexible balloon into a piece of hard plastic.
Essentially, yes. So now your ciliary muscle can contract perfectly, the ligaments can go totally slack, but the hardened lens just sits there. It refuses to balloon out.
It's lost its elasticity.
Completely. The eye becomes permanently focused at a fixed distance, usually for far vision, which is why you see older adults holding menus at arm's length. They need bifocals to provide an external artificial lens for the near work their internal lens can no longer do.
Okay, let's move from the lens to the aperture. Section 5, the pupil and depth of focus.
Right, the pupil. It's the hole in the center of the iris, and it works just like the aperture on a camera.
It can change size pretty dramatically.
From about 1.5 millimeters in bright light to 8 millimeters in the dark. That's about a 30-fold change in the amount of light it lets in.
But it's not just about brightness. The source highlights another really important function, increasing depth of focus.
This is a concept any photographer will know well.
The book has a great diagram, figure 5011, that shows this. When the pupil is very small, what's the advantage?
A small pupil acts like a pinhole. It physically blocks out all the stray light rays that would hit the outer edges of your lens. It only allows a very narrow beam of rays right through the absolute center to pass.
And why is that better?
Because if your focus isn't perfect, those rays hitting the edges of the lens are the ones that cause the most blur. They don't land on the same spot on the retina as the center rays. They create what's called a blur circle.
So by making the pupil smaller,
You physically block those erroneous edge rays, you minimize the size of the blur circle, and the image on the retina gets sharper, even if the focus is a little off.
this explains a life hack I've used my whole life without knowing why it works. If I don't have my glasses on, I can squint, and things become clearer.
You're not changing your lens. You're just creating a smaller aperture with your eyelids. You're forcing your eye to act like a pinhole camera, which increases your depth of focus and makes the system more forgiving of your focus error.
That's brilliant.
It's pure physics.
Well, speaking of focus errors, let's get into them. Section 6. Errors of refraction. What happens when the optics go wrong?
Before we talk about what goes wrong, we should define what's right. Normal vision has a name: emmetropia.
Emmetropia.
It just means that when your eye is fully relaxed, parallel light rays from a distant object focus perfectly on the retina. The power of your lens system perfectly matches the length of your eyeball.
That's the gold standard. So let's break the others. First, hyperopia or farsightedness.
With hyperopia, the problem is usually that the eyeball is too short, or less commonly, the lens system is too weak.
So the light passes through the lens.
But the retina is too close. The light hits the back wall of the eye before it has had a chance to fully converge. The true focal point is somewhere behind the retina.
So the image on the retina is a blur.
Right. But here's the interesting thing about a young person with hyperopia. They can often fake having normal vision
How do they do that?
through accommodation. Remember, their lens system is too weak, but they have a built-in mechanism, the ciliary muscle, to make their lens stronger, to make it rounder.
But wait, accommodation is supposed to be for looking at things up close.
Exactly. But a hyperpopic person has to use a chunk of that near vision budget just to see things far away clearly. They're constantly contracting their ciliary muscle just to see the horizon in focus.
So they're working harder than a normal person just to achieve baseline distance vision.
Constantly. And then when they actually try to read a book, they have to accommodate even more on top of that. They are maxing out their focusing system all day.
That sounds exhausting. It must cause headaches.
A classic cause of eye strain and headaches in children and young adults. And as they get older and presbyopia sets in, they lose that ability to accommodate, and suddenly even their distance vision goes blurry. They can't fake it anymore.
Okay, now for the opposite problem. Myopia. Nearsightedness.
Here, the eyeball is usually too long or the lens system is too strong. Either way, the light focuses in front of the retina. The rays cross over and then start to spread out again before they hit the back of the eye.
And can they compensate for this? Can they relax their lens even more to make it weaker?
No, and that's the key difference. You can't relax a muscle more than fully relaxed. The system is already too powerful, even at its weakest state.
So they're stuck. They can never see distant objects clearly without correction.
Never. But they have what's called a far point. There's a certain distance, maybe a foot in front of their face, where objects are perfectly clear. Anything beyond that far point is blurry.
And now the really tricky one, astigmatism.
Astigmatism isn't about the eyeball being too long or too short. It's purely a shape problem, almost always with the cornea.
This is the egg analogy we talked about.
Exactly. A normal cornea is spherical, like a basketball. An astigmatic cornea is shaped more like the side of a football or an egg. It's oblong.
So the curvature isn't the same in all directions?
Right. A football is curved very steeply around its short axis, but it's much flatter along its long axis.
What does that do to the light?
It means the eye has two different focal points. Light rays entering along the vertical plane might focus at one distance, while light rays entering along the horizontal plane focus at a completely different distance.
So you can't get both in focus at the same time.
You physically cannot. If you use your accommodation to get the vertical lines sharp, the horizontal lines will be blurry. If you adjust to get the horizontal line sharp, the vertical ones go out of focus. It's incredibly frustrating.
Okay, so how do we fix all of these problems? Section 7, correction of optical abnormalities. It's basically applied physics.
It is. You're just adding an external lens to counteract whatever error the eye's internal lens has. It's mathematical cancellation.
For myopia, where the eye is too strong, you need to weaken the system.
So you place a concave lens in front of it. A concave lens diverges or spreads out the light rays a little bit before they enter the eye. That effectively pushes the final focal point backward, right onto the retina.
And for hyperopia, where the eye is too weak, you need to help it out.
So you use a convex lens, you start converging the light rays before they even hit the cornea. That pulls the final focal point forward onto the retina.
And what about astigmatism? This has to be where the cylindrical lenses come in.
Yes, the process is a bit more complex. First, the optometrist finds a regular spherical lens that corrects one of the two focal planes. Let's say they get the vertical lines sharp.
Okay, but the horizontal lines are still blurry.
Right. So then they add a cylindrical lens oriented with the correct axis that adds corrective power only to that horizontal plane without affecting the already corrected vertical plane.
And they have to get that axis of rotation just right?
To the degree. If the error is at 90 degrees, the correcting cylinder has to be at 90 degrees.
The source also gets into contact lenses, and it points out a specific advantage they have over glasses.
This is really neat. When you put a contact lens on your eye, it doesn't sit dry on the cornea. It floats on a very thin layer of your own tears. And the refractive index of tear fluid is almost identical to the refractive index of the cornea itself.
So from an optical perspective, the tear fluid makes the contact and the cornea become one single object.
Exactly. The contact lens effectively replaces the front surface of your cornea. The big, powerful light bend now happens at the air-to-contact lens interface, not the air-to-cornea interface.
Why is that such a big deal?
It's huge for people with irregularly shaped corneas, a condition like keratoconus. Their cornea might be bumpy or cone-shaped. Glasses can't fully fix that. But a contact lens creates a brand new, perfectly smooth front optical surface. The tear fluid fills in all the little bumps and valleys underneath.
It's like paving over a bumpy road.
A perfect analogy. It completely nullifies the underlying anatomical defect.
Let's touch on one last correction. Cataracts.
Cataracts are extremely common, especially in older age. It's simply a clouding of the internal lens.
The proteins inside coagulate.
Just like an egg white turning from clear to opaque white when you cook it. The lens becomes cloudy, and light can't get through to the retina anymore.
And the treatment is pretty direct.
It's surgical. You go in, break up the old cloudy lens with ultrasound, suck it out, and then you insert a new artificial plastic lens in its place.
But the source notes there's a trade-off.
A major one, historically. That new plastic lens is rigid. It can't change shape, so you lose all accommodation.
You're instantly and permanently presbyopic.
Yes, your vision might be crystal clear, but it's fixed at a single focal distance. You'd need reading glasses for any near work. Modern technology is getting better with multifocal implants, but you're still trading a dynamic biological part for a static mechanical one.
Okay, let's move on to how we measure the quality of our vision. Section 8. Visual acuity and depth perception. Everyone knows the term 20/20 vision, but I bet most people don't know what the numbers actually mean.
It's from the Snellen eye chart. The first number is always your distance from the chart, 20 feet.
And the second number?
That's the distance at which a person with normal vision could read the same line you're reading.
So if I have 20/20 vision, it means I can see at 20 feet what a normal person sees at 20 feet. It's the baseline.
Correct. But if your vision is 2200,
that means I have to stand at 20 feet to read the big letter E at the top of the chart.
well, a person with normal vision could read that same letter from 200 feet away. Your vision is 10 times worse than normal. In many places, that's the threshold for being declared legally blind.
What physically limits our acuity? Why can't we have, say, 202 vision and see ants crawling a mile away?
It comes down to the pixel density of our sensor, the retina. The retina is packed with photoreceptor cells called cones, especially in the very center of our vision, an area called the fovea centralis.
And these cones are tiny. The source says they're about 1.5 micrometers wide.
Incredibly small, but they aren't infinitely small. There's a physical space between them. And for your brain to perceive two dots of light as two separate dots, the light from them has to stimulate two different cones, with at least one unexcited cone in between.
If the two dots of light hit two cones that are right next to each other,
your brain just sees it as one single, slightly larger blob of light. That physical spacing of the cones is the hard biological limit on human visual resolution.
So what about depth perception? How does the brain figure out how far away things are? The source lists three main ways.
The first one is the simplest, the size of the retinal image.
Right. Your brain knows a person is about 6 feet tall. If the image of a person on your retina is tiny, your brain computes that they must be far away.
It's all based on a lifetime of learned experience about the sizes of objects. The second mechanism is called moving parallax.
And you can do this with one eye closed.
You can just move your head side to side. Objects that are close to you, like your hand, will seem to move across your field of vision very quickly. But an object far away, like a distant mountain, will barely seem to move at all.
So your brain is comparing the relative speed of objects moving across your retina. Fast movement means close object.
Exactly. It's a hugely important cue for judging distance, especially when you're moving.
And the third mechanism is the one everyone thinks of, stereopsis, or binocular vision.
This is the only one that requires two eyes. Because your eyes are separated by a couple of inches, they each see a slightly different view of the world.
Right, if I hold my finger up in front of my face, my left eye sees more of the left side and my right eye sees more of the right.
And your brain takes those two slightly different images and triangulates them to calculate a very precise sense of depth. But, and this is a really important point, it only really works for things that are close.
Oh, really? I always assumed that was our main 3D tool.
It is for things within, say, arm's reach.
Yeah.
But the book says that beyond about 50 to 200 feet, the difference between what your left eye sees and what your right eye sees becomes almost zero.
So for a distant mountain, both eyes are seeing the exact same picture?
Essentially, yes. At that distance, stereopsis becomes useless, and you're relying entirely on size and moving parallax to judge how far away it is.
Okay, we're in the home stretch. We've done the physics, the lenses, the errors. Now for the plumbing. Section 9, the fluid system of the eye.
Right. We've been talking about the eye like it's a solid camera, but it's really a pressurized globe filled with fluid. There are two main fluids. Behind the lens, you have the vitreous humor.
Which is like a thick gel.
Right. It's mostly structural. But in front of the lens, you have the aqueous humor.
And this stuff isn't stagnant. It's a flowing river?
It is. It's constantly being produced and constantly being drained away. The source says it's formed by the ciliary body at a rate of about 2 to 3 microliters per minute.
And the mechanism for making it is fascinating. It's not just leaky blood vessels.
No, it's an active secretion. The cells in the ciliary body have pumps that actively transport sodium ions into the eye chamber.
And we know from biology that where sodium goes,
Water follows. The positive charge of the sodium pulls in negative ions like chloride, creating a high salt concentration inside the eye. And that osmotic pressure pulls water right out of the blood vessels. That's the pump that keeps the eye inflated.
So that's the faucet. Where's the drain? The eye can't just keep filling up.
The fluid flows from behind the iris, through the pupil, into the front chamber. And then at the very edge, where the cornea meets the iris, there's a spongy meshwork of tissue called the trabeculae.
So it's like the filter over a drain.
A perfect description. The fluid percolates through that meshwork and into a circular vein called the canal of Schlemm.
The canal of Schlemm sounds like something out of a fantasy novel.
It's a real thing. It collects all the aqueous fluid and drains it back into the regular bloodstream.
And this whole system of faucets and drains brings us to our final and maybe most important topic, intraocular pressure and glaucoma, section 10.
Right. That constant production and drainage of fluid creates pressure inside the eye. Normal intraocular pressure, or IOP, is about 15 millimeters of mercury, give or take.
And they measure this with that puff of air test at the eye doctor.
That's one way. The more accurate way is called tonometry, where they numb your cornea and gently press a small, flat instrument against it. The more force it takes to flatten a tiny area, the higher the pressure inside.
So what is glaucoma?
Glaucoma is a disease of high intraocular pressure. The pressure can rise to 60 or even 70 millimeters of mercury.
What causes that? Is the faucet turned on too high?
Very rarely. In almost all cases, the problem is a clog in the drain. The resistance to outflow through that trabecular meshwork increases.
So the drain gets blocked?
It gets blocked. The source says there are normally scavenger cells in there that eat up debris. But if they get overwhelmed by inflammation or debris, the meshwork gets clogged. The faucet keeps running at the normal rate, but the drain can't keep up.
And the pressure builds and builds. Why is that so dangerous? Why does it cause blindness?
The high pressure pushes on all the structures inside the eye. But the weakest point in the entire globe is at the very back, where the optic nerve exits the eye to go to the brain.
The main data cable.
Exactly. The intense pressure physically compresses all the nerve fibers, the axons, in the optic nerve. This blocks what's called axonal flow, the movement of vital nutrients and cytoplasm down the length of the nerve cells.
So the nerve cells literally starve to death.
They starve and die. And once an optic nerve cell is dead, It is gone forever. You cannot regenerate them. This is why glaucoma is called the silent thief of sight. You don't feel the pressure rising, and you don't notice the damage until you've already lost significant peripheral vision, and by then, it's too late.
It's a sobering end to the topic. We've gone all the way from the speed of light in a vacuum to the tragic death of a nerve cell because of a clogged drain.
It really is a remarkable system. The eye is this living camera that has to maintain its own pressure, clean its own drains, and focus by literally changing the shape of its own lens. It's a biological masterpiece.
And it does all of this while sending an upside-down, backward image to a brain that somehow makes sense of it all. It highlights this incredible, delicate balance.
It does. A little bit of protein hardening over time, and you need reading glasses. A little bit of extra debris in that meshwork, and you can lose your vision entirely.
So here's a thought to leave everyone with. We established that the image on the retina is upside down, and the brain is the software that flips it for us. If our neural software is capable of that kind of profound, unconscious editing, how much of what we see is actually optical reality, and how much is just the brain's best guess, its interpretation?
That's the ultimate question, isn't it? The eye sees light, but the brain sees the world. And those two things might not always be the same.
Thanks for listening to The Deep Dive. We'll see you, pun absolutely intended, next time.